Okay. Hi, everyone. I just put a Discord server in the comments right there, so you guys can go ahead and start communicating. Also, I did a meet and greet to get to know, so I can get to know you, and everyone else can, get to know each other on the Canvas. Let me show you. Let me go ahead and also just share the whole desktop. Okay, let's go back to home. So if you go to here, let me delete this, remove. So if you go to here, there is a meet and greet here that I want you guys all to do. So just record a video. I did record it myself to introduce myself, and just pick 2 of these, and then also respond to 3 of your peers. Just to, it's your space. So I want you guys to get to know each other. So this is like a graded discussion. So it is required for part of your grade. You guys all see that on Canvas? It's just like 1 minute, just a little recording of yourself. 90 seconds max. Like I don't want to have like, too long of things. So it's just, of course you can keep on, and you can respond in either video or text fashion to other people's videos.
I have a question.
Go ahead, Brandon.
Wait, we could actually work on that assignment through Canvas? Like, like there's a recording option in there where you could like, or
Yes, there
I didn't see
is.
it, that's why.
Yeah, so there's a couple ways. Either you can record it natively, this button right here. Actually, hold on, let me share it with you guys. Am I sharing? Share my screen. So you can either record it natively by clicking here, and you can either upload a file, or you can record something. I don't know. Let's do FaceTime like this. Now you can watch me watching myself, and then you can then I'll watch you watching yourself watching me. All right.
Got it. Thank you.
Yeah. Or you can also, if you have your own little YouTube channel, you can also like embed a YouTube video in here too. Nice. How you do that? Let's say you had Crash Course History of Science here, and I want to embed that one. So I can embed that by doing Share, going to Embed, and then copying this right here. That'll embed the whole video. If you want to, if you have your, I'm going to start doing that eventually, like embedding YouTube videos, either myself or others, and you do that like that too. Whatever you prefer. Or you can just record it.
Got it. Thank you.
Cool. Other questions? But yeah, it's also built into Canvas. But it kind of like, hey, there's a humans behind there. I know I've heard like there's that report. Apparently there was some, fraud from people trying to enroll. This is also, I was already going to do this anyway, but then I can also kind of see people that they're really there. Okay, so what? Oh, that's fine. Okay, any questions before we get started on chapter 2? Yeah, I'm not expecting like, high production values. Just a short little thing for your introduction video. Oh, yeah. Don't worry about that. The pre-lecture video, I deleted it.
Professor, some people used the email link that you sent before the class started, and there's some people in that Zoom.
Oh,
yeah.
That's the wrong one. Let me go ahead and do an announcement then. Yeah, it changes every day.
Okay, yeah.
Let me go ahead and I was like, where is everybody? Okay, so thank you for letting me know.
Yeah, no problem. We were sitting there like, do we even have class today?
Okay. There we go. Now everyone should start showing up. So, you guys can all join on Discord here. All right. So, let's give a couple more minutes to everyone log into here. So, any questions though? Have you guys started reading? Oh, yeah. So, I've decided to not have a pre-lecture quiz for today. You'll have one for Friday and every one afterward. So, no pre-lecture quiz for today. I was planning on it, but then events kind of caught up with me. So there'll be one for Friday though. Covering chapters 3. Okay. So Friday we'll have a lab. Oop, move this out of the way. Can you guys see that?
Yes.
Okay. Oh, you don't have your book yet? Well, let me hold on one sec. Let me do something for you guys that I was going to do anyway. Yeah, because people have different editions for the textbooks. What I'm going to do is, let me show you when I upload it. So on Canvas, what I just did like a second ago is that you can use this as like a reference copy right here. So you can use that as a reference copy for your textbook. So I know everyone has different editions. This is the editions that I'm going to be referencing problems for like homework 1 for. Homework step 1, the problem's here. Here, you should use this textbook here. Sound good? It's for library reference only. You don't, but yeah, it's really about like just everything. But yeah, if you also want to have a hard copy of the textbook, it's good too. All right, let's go back to it. Okay. Do you see it there, Brandon? So you can start the homework if you need to.
Yeah. Thank you.
Cool. All right, any other questions before we get started today? All right, let me go ahead and share this instead. Oops. Okay, so let's talk about Newton's first law of motion, or the law of inertia. So here is actually where we're starting lecture now. Hopefully everyone's trickled in. I think a couple people still need to come in, but they'll have to watch it later. So let's talk about Newton's first law of motion, inertia. So Aristotle, who had the dominant narrative, that's not how you spell that. in physics in the Western world before the Renaissance. Again, like I said last Monday, it's going to be very Western focused, but you should, of course, broaden beyond this. I'm going to try and broaden as much as I can. But Aristotle, at least with the Catholic Church, was definitely the dominant narrative in the Western world. So believed that the natural state of objects was at rest and toward the ground. However, this view is incorrect. Inertia is a property of matter. So before I, show you this, how would you guys define inertia? What do you guys think?
Something moving and continuously moving.
Okay. So something moving, continuously moving. Okay.
Would it be like something that's still, like has no movement? That's what I don't know.
The property of a thing to resist change in motion?
Guys are all kind of approaching at it. You guys have nothing, no one has said anything wrong yet, but how can these all be consistent? You guys are all correct, but how can they all be consistent? A force that keeps you moving and resistant change. Well, that's close, although you wouldn't really call it a force. It's more of a property of the matter.
Is it like a tendency to remain unchanged or to do nothing? So if something is not doing anything and not moving, it just moves. But if something is already moving, it has a tendency to continue moving.
Victoria, exactly right. Yes. Yes, that's also correct, Marcelena. So what changes it is forces. Getting more exactly, net forces. So yeah, you guys all kind of have an understanding of what inertia is already. So inertia resists changes in motion. So if an object is at rest, it'll remain at rest. If it's in motion, it'll remain in motion in a straight line unless a net force acts on it. So what Aristotle got wrong is he thought the external force of friction represented the natural state of the object, where instead it would continue in a straight line without it. Let's go ahead and consider 3 hockey pucks. One on a table, one on ice, and one on an air hockey table. On a regular table, it slides a certain distance, comes to a stop. On ice, it slides further. On air hockey table, it slides even further. What we're doing is we're reducing the external force on it once it's already at some velocity here. So it's when Newton's first law of motion, an object acted upon by no external net force has a constant velocity, which may be 0, and 0 acceleration. Now, we'll come back and define what those words are, velocity and acceleration, in a bit. But let's go ahead and give you some examples of inertia. So you have like you ever seen the tablecloth trick where you pull it very quickly and all the objects stay there? That's because of inertia. They tend to stay in the same spot. Also, if you ever had a hammer where you take something like this and you smash it down like this to tighten this top here. I'm not going to do it with an actual hammer on my hand. That would hurt. But yeah, you can tighten the top part here as it comes to a stop. It keeps on going into motion. As it keeps on going, it tightens down with a hammer head. Also, you can pull this card here on there, and the coin will fall into the cup. Like, let me do it. One sec. I can do that. I can make this little demo here. Let me go grab that coin. Be right back. Okay, so here's the cover right here. Here's the coin. So you can see this coin right here. If I pull it fast enough, it should stay at rest. That wasn't fast enough. Let's try it again. Okay, and like that. There we go. I yanked it fast enough and the coin stayed in the same spot. And so it just dropped right in. Try it yourself.
So that is inertia, right? Like the movement of like, like that makes another object stays like, I don't know. Never mind.
No, go ahead, Brandon.
Like
kind of.
I was reading right here on the bottom. It says inertia is an action, right? So what you just did was inertia, or like how does that?
No, they're being clever. Inertia in action.
Oh, okay, my bad. Sorry.
They're being clever here. In fact, it's doing the opposite of acting. It's not doing anything.
Right. Okay.
They're doing a little tongue in cheek there. Yeah. But yes, it's basically the tendency for that object, like the coin there, to stay where it started, unless I pulled this slow enough where it had more time for the force to act on it. Okay. Does that make sense, Brandon, and everyone else?
Oh, yeah, thank you.
Cool. So it's more of a property of the object. And how we can measure inertia is with mass. The more mass an object has, the harder it is to change its motion. We'll come back to mass in a bit, because mass is a little complicated. It seems like, oh, it's just a thing. And that is true. It is a thing. It's like how hard it is to change its motion. But when you start really looking at it, it starts getting weird. But we'll come back to that. Also, if you pull it slowly, this string breaks. But if you pull it quickly, this one breaks. I don't have a demo for this, sorry. If they're the same type of string. It's because when you pull on it slowly, this force is bigger than this one here. But if you pull it quickly, it's going to want to stay in the same spot, and this string will snap.
Is that because you have gravity acting on the top one as well as the force you're pushing or pulling?
Yes. One of the reasons, yes. Yeah. Other questions? I love this discussion. You guys are lively. That's why I also kind of like afternoon classes. I'm teaching a morning version of this too, and they're like, coffee. Well, maybe. Or maybe they're just like sleepy, like groggy. So. All right. So let's go ahead and just find something real quick. Equilibrium. It's when for physics at least, because you've probably heard this in terms of chemistry before, right? Equilibrium. So chemical equilibrium. Chemical equilibrium is different from physical equilibrium. It's when the sum of all the forces are zero. So the object does not accelerate and moves in a straight line with constant speed, which might be zero. A force is a push or a pull, and a net force is the vector sum of all the forces on an object. We'll come back to what vector means in a bit. But before I do that, I want to check and see if you guys have questions. So don't worry about what vector is, but it's like a push or a pull. If I pull on something or I push on something. More generally, it's an interaction, but we'll go ahead and talk about it later. Especially in Newton's third law. Right now we're focusing on Newton's first law, which, by the way, wasn't discovered by Newton. It was codified by Newton. He was a smart guy, but he didn't come up with everything. He basically kind of was a codifier and kind of put a lot of pieces together, which is why he got to put his name on the three laws. Any questions, though, so far? All right, let me go ahead and shift over to here. So, Newton combined the observations of many scientists to form his description of the universe. So Copernicus while he wasn't perfect, he did ship, like, was one of the people who shipped it. So Aristarchus kind of thought about, like, maybe the maybe the Earth isn't the center of the universe. But it was, so there was a debate that was kind of put to the back of the mind when everyone said, okay, you know what? Aristotle seems obviously correct, which he wasn't. He was wrong about almost everything. But we kind of like just pushed that debate down until we started realizing, wait, hold on a second. The motion looks really weird if you have the Earth be the center of the solar system, or the universe, as they thought. They thought that the solar system was the universe. So let me show you what that looked like, about how weird that was. But how complicated it got. It looked like... hold on one sec. Let me pull it up. I thought I had it somewhere. Here it is. Okay, let's paste it here. Whoops. I got too many things. Okay. Alright, now we're going to move it like this right here. Ah! There we go. Look at that mess. There's the Earth right there, and you got a whole bunch of things going all over the place. So, this was like a bunch of like weird things happening here. The reason why it looks so complicated is because when the Earth and other planets go around the sun, they sometimes pass each other. And so we had to have them go in weird squiggles to represent that. So this is what it looks like the planets do from our, like, the perspective on Earth, if we consider that the Earth is at rest. And it doesn't make a whole lot of sense unless you have what's called epicycles. I'm not going to get into that because it's not an astronomy class, but suffice to say, the motions get a lot simpler if you have the sun at the center rather than the Earth at the center. Now, Copernicus wasn't perfect. He still had everything orbit in circles, so we still had some weirdness happening. It wasn't until Kepler that it actually was, really codified, and like everyone's like, okay, sure. So partly the reason why Copernicus's model was, pushed back from the church, although he did work for the church, so he's kind of like, until like the Protestant Reformation, when, the Catholic Church and the Protestants were trying to out-Christian each other, he kind of was able to live in this obscurity. But it was only because like Copernicus's models didn't quite fit the data either. It wasn't until Kepler, having ellipses, we'll come back to those, that we actually did fully accept Copernicus's model. Okay. So the Earth is a moving reference frame. Wait, what? Okay. Oh, okay. So Galileo demonstrated. So, sorry, what? Addie, do we have the comparative model after Copernicus? I'm sorry, what do you mean?
You just gave us a geometric model of the orbits. I'm just wondering, if you were saying that was a mess, what it looked like after Copernicus updated the model.
No. That's before Copernicus updated the model. What it looked like afterward, it looked like this. Let me pull it up. Let me just shoot. One sec. That's like the Ptolemaic model that I just showed everybody. What Copernicus had was where is it? Here we are, Copernicus heliocentrism. Here's his model that he drew. Looked like this. So we had all the planets orbit the sun in circles, which is not quite true. And he had the moon orbit the Earth in a circle too. This is what he updated it to be. And he had the known planets of the time: Mercury, Venus, Earth, Mars, Jupiter, Saturn, and this is like the boundary, the stellar boundary, because he didn't know anything else. And it still kind of looked like the stars weren't moving around. Also not correct. So there's a couple things that are wrong, a couple things that are improvements. He has the planets in the right order, which actually, how he proved that they were in the right order around the sun is actually really clever. So while he did, there's certain things he did wrong, getting this order right is very clever. And if you're curious, I can talk about it in office hours about how he did that. It's a bit beyond the scope of this course. But because like the Earth is moving and the planets are moving, how to figure out that order is actually pretty tricky. And then before, then there was like a bridge one, Tycho Brahe, where he had the all the planets orbit the sun, and then the sun then orbit the Earth. This is the Tychonic model, who was like basically the advisor to Kepler. So this is also wrong too. So it was actually when Galileo, no, sorry, when Kepler actually we're actually fully like, okay, this model fits all the data. We're going to talk about that when we talk about orbits, though. Okay, going back to, where were we? Good question. Other questions? That's not the right one. Hold on one sec. Let me hide some stuff. I don't need this. I don't need this. I don't need this. Or this. Or this. Or that. Okay. Now maybe if I share it. There we go. Much simpler. Okay. You guys see this now?
Yes.
Okay, cool. So, let's talk about Galileo. So Galileo almost certainly did not drop things off the Leaning Tower of Pisa, or if he did, it wasn't to prove anything. What he did do is have balls roll down inclined planes, which allows us to kind of like show what happens for free fall. So he demonstrated that all objects in the absence of other forces accelerate toward the center of the Earth at a constant rate, i.e. the distance that an object fell is proportional to the time falling squared. Now, if you ever dropped an object, how long did this take? I don't know. That's kind of hard to do, hard to measure. We might do a lab where we actually do it with your cell phone, but definitely if you try to do it with your own human, since it takes about 1/4 of a second for a human reaction time, it's going to be next to impossible for you to do it yourself. You'd have to have something else do it for you. But what if you're able to dilute gravity? If you had it go at an incline. So normally the acceleration due to gravity is 9.8 meters per second squared. So this is a distance divided by a time squared, lets you know there's acceleration. If you have it at an incline like this right here at 5 degrees, now it actually is diluting the gravity down to this percent right here. This right here means proportional to. So he used little bells ringing and to basically figure out like where things were. And he used like either his pulse to time it because we didn't have good stopwatches yet. Or he might have also hummed little tunes like and and just say, see, because like we're pretty good at keeping time. If you count backwards from 20, 19, 18, 17, it's pretty even. It's not great. I am not like really good at keeping time. I'm trying to get better. It'll be better for my musical abilities. But right now, I know my rhythm is not quite good enough yet to time things. But it was good enough to get a sense of that the distance that it went down the incline was proportional to time squared. So, also things that Galileo got wrong. He didn't realize like, vacuums could be a thing. So that was wrong. But we had to come back for that later. We'll talk about that in a later chapter. But he basically, at this scale, we can still ignore air resistance as it rolls down the incline. And we got to, if it rolls, you can ignore friction, because the friction basically just keeps it rolling. There's some deformation to the incline in the ball that causes some type of rubbing, but mostly it's just to spin the ball as it goes down the incline. All right, questions so far? Hold on. Where'd it go? Uh-oh. Uh-oh. Hold on. I think I need to do something on my Illustrator. I accidentally closed something. How do I reset to standard window? Workspace, painting? Let me do this. Workspace, this, and then do painting? Where are my layers? Sorry, everybody. I don't know where I can put it. Oh, there we go. Okay, got him again. So let's consider inertia, the property of an object to resist changes motion in direction or magnitude. So this is related to mass, which is a measurement of the object's resistance to changes in motion due to a change in force. So we measure that in kilograms, which is the unit of mass. The S is the SI unit of mass. In the US, the equivalent is not pounds. That's a force, not a mass. Mass for the US unit is called the slug. A chunk of something. Why slug, I'm not quite sure, but it's not related to the animal, I think. More probably closer related to bullet slugs and things like that. So a force is going to be a mass times an acceleration, like 4 kilograms times 9.8, which is the acceleration due to gravity. That would be 39.2 newtons. The same thing. 4 kilograms is 2.7 slugs times 32 feet per second squared. Because that's 9.8 meters per second is 32 feet per second. And that gives you about 8.7 pounds. All right. So one way that I can remember, because you probably have a sense of what a pound is. But what's a Newton? Because that's a certain amount of force too. Think of like an apple. An apple's about a Newton. That kind of, yeah, I know. What a coincidence. What I actually didn't come up with it. This textbook actually did come up with that coincidence, and now that it's in there, I'm never going to forget it. That an apple is about a Newton in weight, not in mass. To get mass, you divide it by 9.8. And that gives you the mass. So there's something, we're going to get into talking about what that is, difference between like mass and weight in a second. But I want to just check in with you all. Does everyone make sense that mass is actually resistance to force, not how much it weighs? So how it resists to change motion. Okay. So let's talk about velocity. It's speed with a direction, like 4 kilometers per hour east, or 2 meters per second to the left. This is a velocity. It has a speed and a direction. So we call this a vector. Bigger. We call this object a scale, basically a number with a direction, a vector. Okay. What? What can I draw? Okay, I'll have to underline it later. But yeah, it's important. Vector. Any questions so far? So a vector is something that has a magnitude and direction. Forces are vectors. So another thing where I said changes in motion, that means acceleration. So a force, again, is a push or a pull. And so when you have more than one force acting on an object, you need to find the net force. So here is some applied forces on an object. So you have 5 pulling to the left, and another 5 pulling to the right. The net force is 10 pulling to the right. What's important is you have to identify what direction is the force pulling. Because 5 pulling to the right and 5 pulling to the left gives you a net 0. It matters the direction. So if you have 10 pulling to the right and 5 pulling to the left, you have a net 5 pulling to the right. If a quantity does not have a direction, we call it a scalar. Examples are like mass, volume, speed, and temperature. By the way, we label these vectors with little arrows on top like this. Like this right here, this is a force pulling to the left, right, force pulling to the right, and a force pulling up. Let's call this F1 and F2. How can we find the net force for so one's in one dimension that makes sense. Left and right, you can just add them. But what if they're in 2 dimensions like this? Well, we have to get a little more clever. We have to go ahead and extend this on out, draw a dotted line like this, and a dotted line like this. We can draw the resultant vector from this one to here. We call this the resultant vector. We've added these two together. Okay. This is called the parallelogram method. Parallelogram. Vector addition. So if this was, 4 newtons left, and this one was 3 newtons up, do you anyone happen to know? Let's call this east. East, make it easier. Like we're looking down, east and north. How would we find, what's the length of this vector, the resultant one? Or how would we find it? Think that this vector can be shifted over here. This is a 3, 4.
You square one of those sides.
Okay, we square. So we have 4 squared.
Yes, 16.
And then you're on the right track.
And then we square 3.
Okay, 3 squared.
9.
Okay. And then what do we do? So we have 16 and 9.
Then you add them together.
Okay, which is?
22, 23, 24, 25.
There it is, yeah. And then what do we do?
Not sure after that.
Divide it by 2.
Ooh, almost.
Divide it by 4. Times it by 2.
Wrong operation. We're not multiplying at all. So, Jakeem, you described it almost. What are you describing? Do you happen to know what concept you're describing, by the way? When we, this squared plus this squared?
No, I took this class previously once. I'm just kind of recalling from memory, but I'm not entirely too sure.
Yeah. Well, you're describing something. C squared, yes. So, yes. So, it's what you described, 25, is this side length squared. So, what we got to do to undo the square? Marceline is right. You square root it. Yeah, you guys, this is the Pythagorean theorem that you just described. You walked us through, Kareem. Almost. You almost got there. But yeah, it's kind of funny how it's like buried in our memories sometimes. That what you did was the Pythagorean theorem. It was a squared plus b squared equals c squared. So it's from my choice I picked that on purpose to be what's called the special triangles that are all integers. 3, 4, 5 right triangle. The next one is 5, 12, 13. And the one after that is I'm blanking on it. But yeah, these are special triangles. So this was 4 newtons here. This one was 3 newtons here. So then this one has to be 5 newtons. Because, as Jakeem said, 3 newtons squared. I'm going to put the square in a second. Actually, hold on. I can do this. Squared plus 4 newtons squared equals 5 newtons squared. Let me find it. Come on, highlight it. What's going on? Why are you not cooperating? Okay. So we could find the length of the resultant vector with the Pythagorean theorem. Again, this has been discovered many, many times, so it's not just by Pythagoras. Although Pythagoras did have his math cult. Yes, I said that right, math cult. Well, he was probably didn't drink the, didn't become as cultish as everyone, but he was a strict vegetarian, didn't like to, basically, he was all about beans. So apparently, somewhat apocryphal. Not really sure it's true or not, but it sounds that he, supposedly he was being chased out as a cult leader, and they didn't want the cultists around out of a city, and he apparently could have ran through a field of fava beans, but he went around it, and so they caught up to him and he killed him. That's supposedly how Pythagoras died. But it may be up there with the Eureka story of Archimedes running through the streets naked. We don't know if that actually happened, but they both were weird in that way. So, scientists being weird since for thousands of years. Okay, Pythagorean theorem. I just want to go say yeah, be as weird as you want, because people have been weird for forever. All right. Questions on this? Generally, in this class, I'll have vectors that either be in the same direction or opposite directions, or that they're perpendicular to each other. There's more general ways of doing this, but since this is a conceptual class, I'm going to be only these two cases. If this is physics 6 or 8, you would do the more general case, or 21, we do the more general case, but for this is as much as we're going to do. Any questions?
Yeah, I have a question.
Sure, go ahead, Brandon.
So whenever you have a vector like that, it means you have forces on all sides of the
Just two. These two.
All right.
We just did these dotted lines out here to figure out what's the total one going to be. So we made it into a parallelogram. I mean, it's a rectangle because in this case, but in general it would be a parallelogram. And that would help you find the resultant one, because it could look more like a parallelogram. Go ahead, Brandon.
No. I got it. Thank you.
Cool. Okay. So, let's say if you had a 45-degree angle, some special triangles. If it's at a 45-degree angle of a right triangle, this will have each side length will be the same. It could be 1, or it could be some multiple of 1. So this is 1, 1, and this will be the square root of 2. Okay. And the other one is going to be the 30, 60, 90 right triangle, where it's going to be x, x root 3, and 2x. So here's some special triangles: 3, 4, 5, and 5, 12, 13. Beyond what's on this and the Pythagorean theorem, you won't need anything else. A squared plus b squared equals c squared. So the equilibrium rule is that the sum of all these forces on an object have to equal 0. That is going to be no acceleration and no change in velocity. let's go ahead and look at this in practice here. So, in this case, you have a person standing here. So the person has a force of gravity acting on him. The scaffolding has a force of gravity on it, and this person also has a force of gravity on them. These two ropes have to also have support these two people and the scaffolding itself. So these two forces have to act to these ones here if the scaffolding is staying in equilibrium. So it means sum of, but it's the particular kind of sum. Here's a question. In this diagram here, which rope, so here there's two little scales right here, which one will read larger?
I'm going to say the shorter one.
Why?
I don't know, it just seems like it's tighter.
Wait, what was the question again?
Which rope has more tension, the left rope or the right rope?
I think the left rope.
Mm-hmm. Okay.
Why?
Why? Yes, why?
I think there's so both of them are being pulled by gravity and then directional force of left, right to find the center balance, right?
Mm-hmm.
And I think that one's being pulled more out of the way, so it's going to have more momentum coming back in, and so that the suspension tension is further for the mass of the person instead of the other one, which is more vertical and it only has the vertical axis of force as the primary deviation.
I think the right rope, as someone said before.
Why do you think that?
If you think of it as just a real life principle, if you have a shorter rope and you pull it, and you have a longer rope and you pull it from a distance, the shorter rope will have more tension because you have less pull, you have less room to pull versus a longer rope. You kind of have more room.
Okay. Any other thoughts? You've all said pieces of things that are correct. No one said anything that's flatly correct or flatly incorrect. You're all kind of like circling around the answer for different reasons.
Say it's the right one too.
Okay, let's go ahead and...
Does it have to do with the person's weight or anything like that?
Yes.
Maybe because it's closer to it. I don't know. Yeah, when I picture it in my head, it's like both of them could be like the same. Like, you know, they could have the same tension.
Yeah. So they could, but actually, it's the right one that has more tension. So your instinct, Addie, about like, oh, you got to have like these forces to the left-right balance is right. That's correct. But you can see that the part that's in the left-right direction is actually, to get the same left-right direction, actually has to be bigger when it's pulling straight up. Now, because here's like the force pulling up here and the force pulling to the right here. So what's true about this, it has to have the up-down part equal this one right here. And the way that can work is having a small one here and a large one here. Now, probably you might be thinking of an idea. Where is my? Okay, maybe you might be thinking, Addie, of like, you know, whether you have something in tension having a small one versus a large sag. Now that would be true. The one with a large sag would be less tension.
I'm specifically thinking about hammocks, actually. Yes.
Exactly. So when you cinch it up more, you have less sag. But that's not what's happening here exactly. It's that these two forces to the left, right cancel, and this part here, like it's done in dotted green lines here, this force, net force, has to balance out this one. So, yeah. You guys, like I said, you guys were all saying things that were right, but we all got close. This one was tricky. Not gonna lie. This would probably be a little bit too advanced for you guys to say on an exam, but like just something to think about. I'll have these kind of conceptual ideas, because I could have like really hard questions on the exam. I won't be like, this is a little too hard for an exam, but you know, point of discussion for this class though. Any questions about this? How we're gonna have this force has to be balanced by this, and it has to be along this one and along this one. So you can see that it's going to be more along this than this. So it's more newtons on the left. All right. All right. Okay, I think this is a good time to take a 10-minute break, though. You guys have any questions, though? All right, let's come back at 3:09. See you guys then. Okay, we're back. So let's go ahead and get back to it. Let me go ahead and share my screen. Okay. Zoom in. Shrink this a little bit more. Let's talk about support forces. So what we're talking about here is the difference between mass and gravity. So consider like a book lying on a table. It's in equilibrium. It's not accelerating upward or downward. Well, at least from Newton's perspective, it's in equilibrium. Come back to that when we talk about general relativity. But for now, we're going to consider this in equilibrium. So, from Newton's perspective, the book is in equilibrium. There's no net force on it. There's a force of gravity pulling down and a normal force pushing up. This normal force is what we actually experience as our weight. You can think of it like a spring, because actually what is happening is the book is deforming the table slightly, just like how you would deform a spring when you push down on it, like this. So the table deforms slightly and pushes the book up. And just like when you stand on a scale, the scale reading is your weight, not the force of gravity. Now, why am I drawing this distinguishing? It depends if you're in an accelerated reference frame or not. So like, let's say we had this scale not, just standing on the ground here, but let's say we went in an elevator. And let's say the elevator accelerated upward. Now the scale reading will be higher. Like if you're in the, let's say, also consider you're standing in the scale and the elevator starts accelerating downward. The scale reading gets less. And so you actually feel heavier and lighter in that elevator, right? You ever felt like, when the elevator goes up, you start to sink down a little bit if you don't really anticipate it? Same thing, you start to feel like, oh, if you start accelerating downward. We'll get in chats. Okay, yeah. You can see it now? Okay. We'll come back to this later, but I just want to introduce the concept that the scale reading is your weight, not the gravitational force. Well, actually, when you talk about general relativity, we do away with that gravitational force entirely, but let's come back to that at the end of the course. I'll allude to it, but basically, when I said, that's why I said in Newton's perspective, the book is in equilibrium, because in Einstein's perspective, it's not. But we're going to come back to that. If you want a little sneak preview, I think Veritasium has a really good video about the force of gravity. Has anyone watched that Veritasium video? No? Okay. But yeah, there's one about the force of gravity, if you're curious. About what I'm alluding to, you can watch Veritasium has a really excellent video about how gravity is not a force. Here, let me give it to you guys. The YouTube video. So, let me go ahead and video briefly. This one here, I'm going to put it. That one. So I'm going to go back to it. Our regular thing, though. You can watch that on your own now. Any questions on this, though? About how, the support force is the normal force? Like this book right here. So that's why you don't fall through the table, is a support force, from both perspectives. The reason why you don't fall through the table is there's a normal force pushing back. All right. Let's start with equilibrium of moving things. Because, like a couple of you guys said, so you can be in equilibrium if you're at rest. We can also be in equilibrium if you're in constant motion. So if this person's pushing on a block right here with a 75 Newton applied force, and there's a 75 Newton friction force pushing back, this one has 0 net force, and so there's no acceleration. So here's a question from the book. An airplane flies at a constant speed at a horizontal straight path. In other words, the plane is flying in equilibrium. Two horizontal forces act on the plane. One is the thrust of the propeller forward as it pushes forward. That pushes it forward, and the other is the force of air resistance that acts in the opposite direction. Which acts greater? Remember, it is going forward.
The air resistance?
Nope. Nope. Not the thrust of the propeller either. They have to be the same. Otherwise, it'd either slow down if, in what Grant said, if the air resistance is bigger, or it would speed up, what Marcelena said, if the propeller was bigger. And since it's in equilibrium, they have to be the same. So here it's that the sum of the forces have to be 0 because we're in equilibrium. The sum of the forces must be the 0 because we are in equilibrium. All right. Let's watch a video that actually has like an old-timey video I'm going to show you guys that has some really cool stuff about frames of reference and the moving Earth. And then we'll start a little bit of chapter 3 because we actually need to start a little chapter 3 because Friday we're going to do a lab. Let me go ahead and pull it up here.